a look at the pencil. It is straight, as we all can see. Now we'll put it into a glass of water. What happened to the pencil? It is bent now. Is the pencil really bent? No, it just appears to be. You can see that when you take the pencil out again. The apparent bending of the pencil is a result of a property called refraction. In this lesson, you will learn about refraction and concepts associated with it. At the end of this lesson, you will be able to define refraction of light, identify the terms related with refraction of light, state the laws of refraction, define refrangibility, define absolute refractive index of a material, state Snell's law and verify it experimentally, define critical angle, define total internal reflection and discuss its applications, and find lateral and vertical shifts in refraction. When a ray of light propagates from one medium to another, for example, from air to water, its velocity changes, and hence it deviates from its path. This tendency of light to deviate or bend at the point of separation of two media is called refraction. Let's return to our original question. Why does the pencil bend when immersed in water? What happens to it? Actually, the pencil doesn't really change its form at all. The apparent bending of the pencil occurs due to refraction of light as it passes from air to water. The light bends at the surface of separation of the two media. In fact, any object partly immersed in a different medium will appear bent. Let's examine refraction of light as we saw it in the pencil and look at various terms associated with this phenomenon. The ray of light that is incident on a surface is called the incident ray. The ray that deviates at the point of incidence due to a change in medium is called the refracted ray. The perpendicular line between the two media is called the normal. The angle formed between the refracted ray and the normal at the point of incidence is known as angle of incidence. The angle between the normal and the refracted ray is known as angle of refraction. Let us consider a light ray traveling from air to water. As you can see, the ray of light bends towards the normal. The incident ray and the refracted ray are in the same plane. These observations form the basis of the laws of refraction. The first law of refraction states that when a light ray passes from a rarer medium to a denser medium, it bends towards the normal. When it passes from a denser medium to a rarer medium, it bends away from the normal. As per the second law, the incident ray, the normal at the point of incidence, and the refracted ray all lie in the same plane. The ability of light to bend when passing from one medium to another is called refrangibility. Let's compare two situations where we observe the bending of light. When light passes from air to water, when light passes from air to glass, you can see that light bends or deviates differently in both cases. That is, the angle of refraction in both cases is different. The deviation of light depends upon the nature of the two media and the optical density of the two media. The optical density of medium is determined by a property called refractive index. The ratio of velocity of light in the first medium to that in the second medium is known as the refractive index of the second medium with respect to the first medium. The refractive index remains constant for a given pair of media. Further, the ratio of velocity of light in air or vacuum to that in a medium is called the absolute refractive index, mu, of that medium. If the refractive index of a medium is relatively higher, the velocity of light rays in that medium will be relatively lesser. For example, recall the bending of the pencil in water. As the refractive index of water is more than that of air, light travels at a lesser speed through water as compared to air. Thus, the pencil appears bent. It is difficult to determine the velocity of light in each medium. Therefore, another method of determining refractive index of media was needed. Wilbrord Snellius, a Dutch mathematician, discovered the relationship between the angle of incidence and the angle of refraction for two given optical media. On the basis of this knowledge, he proposed a law to measure the refractive index of a material. This law is known as Snell's law. According to Snell's law, the ratio between the values of the sine of the angle of incidence and the sine of the angle of refraction for two given optical media is a constant quantity. Snell's law can be verified through an experiment using a glass slab, a white paper, and some pins. For this experiment, we put a glass slab ABCD on a white paper and fix this paper on a wooden board. Next, we mark the boundary of the glass slab with a sharp pencil and then remove the slab. Then we mark a point P on side AB and draw a normal NP-N1. In the next step, we fix two pins, P1 and P2, at an angle of 30 degrees to the normal in a vertical position. A minimum of 5 centimeters of distance is kept between the pins to ensure that the points are easily distinguished. Now the glass slab is placed back on the paper the way it was before. On looking through this glass slab from side CD, the pins P1 and P2 appear at positions L1 and L2 due to refraction. Next, we fix two other pins, P3 and P4, where they are in line with the images L1 and L2 of the pins P1 and P2. In the next step, we remove all the pins and draw small circles around them. We join P3 and P4 to meet CD at R. After joining PR, we measure the angle of incidence P1-PN and the angle of refraction N1-PR. Finally, by finding their sine values and applying it in the formula, we find mu is equal to sine I divided by sine R. If the experiment is repeated using different values of angles of incidence, the refractive index remains the same. Thus, this experiment verifies Snell's law. The principle of Snell's law is valid regardless of the direction of the light. If a ray travels from medium 1 to medium 2 along a certain path, it will follow the same path while traveling from medium 2 to medium 1. This is known as the principle of reversibility. Now let's consider a case where a light ray passes from a denser medium to a rarer medium and bends away from the normal. If the angle of incidence I in the denser medium is increased, then at a particular angle of incidence, the refracted ray propagates along the boundary of the two media. This angle of incidence is called critical angle of the given denser medium with respect to the given rarer medium and is denoted by dCr. As the refracted ray travels through the surface, it makes an angle of 90 degrees with the normal. Thus, we can say that at the critical angle, the angle of refraction is 90 degrees. If the angle of incidence is more than the critical angle, the refracted ray bends by more than 90 degrees. That is, it gets reflected back into the same denser medium. This phenomenon is known as total internal reflection. This property of light is responsible for an interesting natural phenomenon, mirages in deserts. In deserts, we sometimes see mirages where images of distant trees are visible when the temperatures are high. In nature, Images of trees are formed only in water. We may therefore be tricked into believing that we are near water and trees. However, these images vanish as we approach the location. A mirage is caused by the total internal reflection of light. When the sun is high in the sky, the sand gets hot before the layers of air above it. Light rays from trees travel from an optically denser air layer to a rarer layer, and hence bend away from the normal. This bending continues till a stage is reached where the angle of incidence becomes greater than the critical angle, and total internal reflection takes place. The totally reflected rays that reach the eyes appear to come from a point on the ground, where the image of the tree is formed. Thus, we see inverted images of trees even though there is no water around. When a ray is incident on the surface of a transparent medium such as glass, its position changes laterally when it goes out of the medium. This shift of the refracted ray laterally is called a lateral shift. Now let's derive an expression for the lateral shift in a glass slab. Consider refraction of light through the glass slab ABCD shown. Light ray PQ incidents at Q on the face AB of the slab and refracts on passing from air to glass. In the glass, the refracted ray QR incidents at R on the face CD of the slab. At R, the ray again refracts into air and emerges as RS. Thus, RS is the emergent ray. In the absence of the glass slab, the ray PQ would have traversed along the dotted line QU as shown. Since the faces AB and CD of the slab are parallel, the ray RS is parallel to PQ. Hence, in total, the deviation of the light ray is 0, but the ray is shifted laterally. The perpendicular distance between the emergent ray RS and the incident ray PQU is the measure of the lateral shift and is denoted by S. RU represents this lateral shift in the figure. NQT is the normal at Q on the face AB of the slab. QT is the thickness of the slab, represented by T. Angle PQN is the angle of incidence of the light ray in air, represented by I. Angle TQR is the angle of refraction of the ray in the slab, represented by R. Hence, angle RQU represents the angle of deviation of the light ray when refracted into glass. It is equal to I minus R. Now consider the right triangle QRU. In this triangle, sine of I minus R is equal to the ratio of S to QR. Thus, QR is equal to the ratio of S to sine of I minus R. This gives you equation 1. Now consider the right triangle QTR. In this triangle, cosine of R is equal to the ratio of QT to QR, which is equal to the ratio of thickness T of the slab to QR. Thus, QR is equal to the ratio of T to cosine of R. This gives you equation 2. From equations 1 and 2, we get the lateral shift in the slab as S is equal to T multiplied by sine I minus R divided by cos R. Besides lateral shifts, you can observe vertical shifts because of refraction of light. For example, when you look into a swimming pool, you generally feel it looks shallower than it really is. This is caused by a vertical shift in the rays refracted when changing media between air and water. You can verify the phenomenon of vertical shifts through an experiment. Put a coin at the bottom of the trough containing water to a depth h. When viewed from above, the bottom of the trough and the coin appear to be raised. This change in the perceived depth of an object in a denser medium as observed from a rarer medium is known as vertical shift. Refractive index mu of a material is the ratio of real depth h to apparent depth h dash. Thus, apparent depth is the ratio of real depth to the refractive index. Vertical shift, denoted as delta H, is equal to the difference of real depth and apparent depth. By substituting the values of h and h dash, we get the expression of vertical shift as h multiplied by 1 minus 1 divided by mu.